Category O, Lecture 17, Shuffling Functors. Let us start with our setup. Consider a semi-simple finite-dimensional Lie algebra G over the field of complex numbers and fixed a triangular decomposition of G into a direct sum of the negative part n minus, the Cartan subalgebra H, and the positive part n plus. Let W denote the Weil group of G. Associated to this triangular decomposition, we have the corresponding Bernstein-Gelfand-Gelfand category O, and we can consider its principal block O0. We know that simple objects in O0 are indexed by elements in the Weil group. We denote by LW the simple highest weight G module with highest weight W dot 0. We have other structural modules in category O. We denote by PW the indecomposable projective cover of LW, by IW the indecomposable injective envelope of LW, by delta W the Vermont module with highest weight W dot 0, by nabla W the dual Vermont module with highest weight W dot 0, and by TW the indecomposable tilting module with highest weight W dot 0. We know that the Grothendieck group of the principal block of category O is isomorphic to the free abelian group with a basis given by elements in the Weil group. This isomorphism is given by sending the class of the Vermont module delta W to the element W. We further have the Hecke algebra of W with standard basis HW. The Hecke algebra H also has the so-called Kazhdan-Lustig basis, which we denote by HW underlined. We further can consider the graded lift of the principal block O0. We denote this graded lift by O0 upper Z. And we fix standard graded lifts of all structural modules in the principal block. We know that the Grothendieck group of this graded lift is isomorphic to the Hecke algebra via the isomorphism which sends a class of the graded Vermont module delta W to the element HW in the standard basis of H. And also another property of this isomorphism is that it intertwines the shift of grading with multiplication with the variable v, which belongs to the Laurent polynomial ring used to define the Hecke algebra H. Further, we have the monoidal category P00 of projective endofunctors of O0. And this category admits a graded lift, which we denote by P00 upper Z. Indecomposable projective functors are naturally indexed by elements of the Weil group. So we denote by theta W the indecomposable projective functor, which is uniquely defined by the property that it sends the dominant projective module PE to the projective module PW. And this isomorphism is valid both in the graded and in the ungraded versions. The split Grothendieck ring of the monoidal category P00 is isomorphic to the integral group algebra of the Weil group. The split Grothendieck ring of the graded lift of this category is isomorphic to the Hecke algebra. Both these isomorphisms are defined by sending the class of the indecomposable projective functor theta W to the element HW underline of the corresponding Kazhdan-Lustig basis. Let us now talk about translations through walls. This is a special class of projective functors. Fix a simple reflection S and consider a dominant integral weight which is singular and whose singularity is exactly the group consisting of the identity E and our simple reflection S. Then we have the corresponding block O lambda S of O, which is now a singular block. From Bernstein and Gelfand classification of projective functors, we have the indecomposable projective functor theta S on, which is also called translation to the S wall, which sends the dominant Vermont module delta E in O0 to the dominant Vermont module delta lambda S in O lambda S. We also have the indecomposable projective functor theta S out, which is usually called translation out of the S wall, and this functor says the dominant Vermont module delta lambda S in O lambda S to the indecomposable projective module PS in O0. The indecomposable projective functor theta S is defined as a composition of theta S on followed by theta S out, and this theta S is called translation through the S wall. And we know that these two functors, theta S on and theta S out, are biadjoint, so they are adjoint in both directions. As a consequence of this biadjointness, we have adjunction morphisms as follows. So we have the adjunction morphism adjunction lower S from the identity on O0 to theta S, and this is a graded morphism of degree 1. We also have the adjunction morphism adjunction upper S from theta S to the identity, and again this is a homogeneous morphism of degree 1. Also note that we also have adjunction morphisms on the level of O lambda S. There is an adjunction morphism from the identity of O lambda S to the composition of theta S out followed by theta S on, and there is an adjunction morphism from this composition to the identity of O lambda S. In fact, one can show that the composition of theta S out followed by theta S on is isomorphic to the direct sum of two copies of the identity functor on O lambda S shifted by 1 and -1 in the gradient. Now we are ready to define Shuffling and co-shuffling functors associated to simple roots. They were first defined by Kevin Carlin in his paper from 1986. So the shuffling functor Cs associated to S is defined as a cokernel of the adjunction morphism adjunction lower S from the identity on O0 to theta S. The co-shuffling functor Ks associated to S is defined as the kernel of the adjunction morphism adjunction upper S from theta S to the identity on O0. Please note that from the snake lemma, it follows that the functor Cs, being the cokernel of a natural transformation between exact functors, is right exact. And similarly, the functor Ks is left exact. And also directly from the definitions, we see that the functor Cs comes together with a natural transformation from the translation functor theta S to Cs, and similarly the functor Ks comes together with a natural transformation from this functor to theta S. The proper reference for this definition is the paper Extensions of Vermont Modules by Carlin from 1986. In that paper, Carlin already notes that Cs and Ks is an adjoint pair of functors. To prove this, we consider the following diagram in O0. So in this diagram, we have the following. Both horizontal rows are given by definitions of the functors Cs and Ks, and therefore they are exact. So the first row is obtained if you apply the contravariant left exact functor home into Y to the right exact sequence which defines the functor Cs. And the second row is obtained if you apply the covariant left exact functor home from X to somewhere to the left exact sequence which defines the functor Ks. The middle vertical row is given by the self-adjointness of the functor theta S. So the right vertical row is just the identity. And it is very easy to check that the solid square commutes. So this is an exercise. Consequently, the commuting solid square on this picture induces the vertical dotted arrow as shown on the diagram, and from the 5 lemma we obtain that this arrow is an isomorphism. So this proves the claim. So let us look at the SL2 example. Consider the Lie algebra SL2, in which case the while group just consists of the identity and the simple reflection S. So here is the graded picture of all indecomposable modules in the principal block of category O for SL2 and their translations through the S wall. So the simples S and E are concentrated in degree 0. The projective module PE has top in degree 0. The tilting module TE has middle in the degree 0. And the injective module IE has socle in the degree 0. So all other indecomposable modules can be obtained from these modules using isomorphism and shift of grading. So the functor theta S kills LE and maps LS to the tilting module. So theta S LS is just the tilting module, and theta S LE is 0. So theta S PE will be the tilting module but shifted by 1 because S here was in degree 1. So theta S TE will be two copies of the tilting module, one coming from this S and one coming from this S. And so they are shifted by 1 up and 1 down. And finally, theta SIE will be the copy of the tilting module shifted one step up because it comes from this S in degree -1. Here is then the picture of shufflings and co-shufflings of these modules. So if we take the natural transformation from LS to its translation of degree 1, the cokernel will be exactly the injective module IE. So this is CS of LS. Dually, if you take the natural transformation from this translation to LS of degree 1, the kernel will be exactly the projective module PE. The shuffling and the co-shuffling of LE is 0 because theta kills L0. Now, if we take PE, so the natural transformation from here to this of degree 1 has S as the cokernel in degree 0. And in the opposite direction, the natural transformation from here to here has kernel ES, starting from degree 1. Well, for TE, we double it here, so it's clear that both shuffling and the co-shuffling will be just one copy of this TE shifted one step up and one step down. And finally, for the injective module, we have the natural transformation, which sends the top S here to the socle, and the cokernel is this injective shifted by 1 in degree. And for the co-shuffling, we have the natural transformation, which is surjective, and the kernel is just S living in degree 0. So this is the SL2 example. Let us now discuss how shuffling and co-shuffling functors interplay with the simple preserving duality star on O0. So the claim is that Ks is actually isomorphic to conjugation of Cs by the simple preserving duality. To explain why this is true, we start from the right exact sequence, which defines the functor Cs, and apply the simple preserving duality to this sequence. So if we do that, we get a left exact sequence, of course, and here we can use that the simple preserving duality commutes with the projective functor theta s and the identity, and there is a unique up to non-zero scalar natural transformation from theta s to the identity, which is homogeneous of degree 1. So this follows from Bakelin's description of homomorphisms between projective functors. From this, it follows that the composition of Cs followed by the duality is isomorphic to the composition of the duality followed by Ks, which is exactly what was stated in the proposition. For details, I refer to my paper with Katarina, which is called Translation and Shuffling of Projectively Presentable Modules and the Categorification of a Parabolic Hecke Module from 2005. Let us now discuss shufflings of Vermont modules. Recall that for any element in W and any simple reflection S, we have the following short exact sequence. So in the case when Ws is greater than W, then theta s delta W surjects onto delta Ws, and the kernel is delta W shifted by -1. In the case when Ws is smaller than W, then theta s delta W surjects onto delta W shifted by 1, and the kernel is delta Ws. It is easy to see that the left map in the first sequence and the right map in the second sequence are in fact given by a junction, of course up to a non-zero scalar. From this it follows that In the case Ws is greater than W, then the S shuffling of delta W is equal to delta Ws, directly from the first sequence. If Ws is smaller than W, then the co-shuffling Ks of delta W gives delta Ws. So this is directly from the second sequence. If Ws is smaller than W, then the class of Cs delta W in the ungraded Grothendieck group of O0 is equal to the class of delta Ws. Finally, if Ws is greater than W, then the S co-shuffling of delta W is isomorphic to delta W, again up to shift of grading. For example, for the Lie algebra SL2, we have that the S shuffling of delta E is equal to delta S, so we saw this computed explicitly on the previous slide, and the S shuffling of delta S gives nabla E. We also have that the S co-shuffling of delta E is isomorphic to delta E up to shift of grading, and the S co-shuffling of delta S gives delta E. Let us now talk about shuffling of simple modules. Recall that for an element W in W and a simple reflection S such that Ws is greater than W, the module theta S applied to LW is 0. In the other situation, that is when Ws is smaller than W, we have that the module theta S LW has simple top isomorphic to LW and simple socle isomorphic to LW. And then we have what is called the Janssen's middle, which is the quotient of the radical of this module by its socle. And this module is semi-simple, and it contains all subquotients Lx, where xs is greater than x, with multiplicity given by the Kazhdan-Lusztig mu function mu wx. So in particular, it follows that the simple module LWS appears in Janssen's middle with multiplicity 1. A consequence from this is that in the case when Ws is greater than W, then both shuffling of LW and the S co-shuffling of LW, they both are 0. If Ws is smaller than W, the S shuffling of LW is just the quotient of theta S LW by its socle. Dually, if Ws is smaller than W, then the co-shuffling of LW is just the radical of theta S LW. For example, in the case of SL2, both shuffling and co-shuffling of LE are 0, and if we shuffle LS, we get nabla E, and if we co-shuffle LS, we get delta E. The next important property of shuffling functors is the fact that they satisfy braid relations. So the statement shuffling functors satisfy braid relations. So this means the following: if we take any pair of simple reflections S and T, which satisfy the braid relation of the form S, T, S, and so on is equal to TST and so on, in the group W, then the corresponding shuffling functors satisfies the same lengths braid relations. So CS, CT, CS, and so on is isomorphic to CT, CS, CT, and so on. So we give a proof for the long braid relation in type A. So let us assume that STS is equal to TST. So this is the type A braid relation, the long one, not the commutativity. So in this case, we know that the composition of theta S, theta T, theta S is isomorphic to the direct sum of theta STS with theta S. Therefore, from the definition of shuffling functors, it follows that the composition CS, CT, CS is the quotient of this direct sum by the image in this direct sum of the projective functor theta S theta T times the identity plus theta S identity theta S plus identity theta T theta S. And this should be a quotient under a natural transformation of degree 1, which is unique up to scalar for each pair of direct sums. It is easy to observe that for the middle term in the second direct sum, which is theta S times theta S, and which is isomorphic to theta s plus theta s shifted by 1 and minus 1. So the part which is shifted by 1 covers, by the degree 1 natural transformation, the theta s summed in the first direct sum. From this it follows that the product which we want, Cs, Ct, Cs, is actually the quotient of theta s Ts by the image in it of the direct sum theta s theta t plus theta t theta s under a unique degree 1 natural transformation, so it's unique for each direct summand. And this description is now symmetric in S and T. So because of this symmetry, the claim of the theorem follows. So now we can define shuffling and co-shuffling functors associated to any element of W. Consider an element W in W and fix a reduced expression of this element. W is equal to the product of simple reflections S1, S2, and so on, Sk. So we define the shuffling functor Cw as the composition of Cs1 followed by Cs2 and so on, followed by Csk. Note that here we reversed the order of elements in the reduced expression due to the fact that the action of projective functors on category O is a right action. From the definition, it looks as if Cw depends on the choice of the reduced expression. However, the claim is that it does not depend on this choice of the reduced expression, of course up to isomorphism. And this follows directly from the well-known fact that any pair of reduced expressions are connected by a sequence of braid moves. And as we saw on the previous slide, shuffling functors satisfy braid relations. Another consequence is, of course, that co-shuffling functors also satisfy braid relations. This follows by adjunction from the braid relations for shuffling functors. And therefore, we can define the co-shuffling functor Kw also as the composition Ks1 followed by Ks2 and so on Ksk. So let us consider as an example all shuffled simples for the Lie algebra SL3. So recall that for this Lie algebra, if we translate Ls through the S wall, we get the module with simple top S, simple socle S, and the Janssen middle is St plus E. And if we translate the simple module LTS through the S wall, we get that the top is Ts, the socle is Ts, and the Janssen middle is just T. And swapping the S and T, in these formulas we can get the translations of simples through the T wall. So here is a table of all shuffled simples. So the shuffling with respect to the identity is the identity, so it's not written here. So if we shuffle by S, so the identity always dies because the identity simple module is killed by any non-identity indecomposable projective functor. So now if we shuffle Ls by Cs, so we take S, the degree 1 morphism to theta S Ls, and we should take the cokernel. So we get the module with top S and socle St plus E. So if we shuffle Lt by S, we get 0 because Lt is killed by theta S. And similarly, Lst is killed by theta S. So if we S shuffle LTS, then we should take the cokernel of the map from Ts to here, and then we get the module with top Ts and socle T. And if we S shuffle the module LW0, we get the module nabla St. So this follows from the properties that LW0 is a nabla, and because of the connection between shuffling and co-shuffling functor using duality, and the fact that we know what co-shuffling does on Vermont modules, we can compute the shuffling of the dual Vermont module nabla W0, and we will get nabla St. So the shuffling of dual Vermont modules are always dual Vermont modules, up to graded shift. So swapping the role S and T, we get the second column in this picture, the T shufflings. So the interesting part is, of course, then what is the ST shufflings. So for the LE, it's 0. So if we try to compute the ST shuffling of LS, we need to compute the T shuffling of the S shuffling of LS. So we need to compute the T shuffling of this module. And now this means that we have to take the cokernel of the map from theta T, which the only thing which will not be killed is this LST. And if we take the cokernel, this S will cover the middle part and we get ST back. So the ST shuffling of LS is just the simple LST. So the ST shuffling of LT is 0 because it's already 0 here. And the ST shuffling of ST is 0 because it's already 0 here. And now to get the ST shuffling of TS, we need to take the T shuffling of this. So we translate through T, and then we get T here. This TS is equivalent to here. So the cokernel will be this part with T and S swapped. So it will be top T and socle E. And again, if we shuffle a dual Verma module, we get a dual Verma module. We just multiply T on the right. So shuffling nabla ST, we get nabla S. And this column we get by just swapping S and T in the previous column. And finally here, CW0 of all simple modules you will get 0. So because of these zeros which appear here. And the shuffling by the longest element. So we need, for example, to shuffle by S this nabla, we get nabla E. So this is how one computes the SL3 example. Now I want to talk about the derived versions of shuffling and co-shuffling functors, and for this we need some new definitions. So I want to define the other side parabolic subcategory in O. Let S be a simple reflection. Denoted by XS, the third subcategory of O0 generated by all simples LW such that WS is greater than W. This is exactly the condition when theta SLW is 0. Of course, directly from the definition, we have the natural exact inclusion IS from XS to O0. So this exact inclusion has both left and right adjoint. We denote by zeta S R the left adjoint of IS, and this is what one could call the other side Zuckerman functor. So this functor takes the maximal quotient of a given module, which belongs to our category XS. So here R stands that this is the parabolic category on the right, the right action of W on itself. And if we look at the definition of the co-shuffling functor, we will see that this functor is isomorphic to the cokernel of the natural transformation adjunction upper S. Dually, we can define the functor Z hat S upper R, which is the right adjoint of IS, and this is the other side dual Zuckerman functor. So this functor takes the maximal submodule of a module, which belongs to XS. And again, if we look at the definition of the shuffling functor, we observe that this functor is isomorphic to the kernel of the natural transformation adjunction lower S. So now let us consider the left derived of the right exact functor CS. So this is a functor LCS, which is an endofunctor of the bounded derived category of O0. We claim that this functor has the following cohomology functors of positive degree. The cohomology functor LICS vanishes for all I greater than 1, and the first cohomology functor L1CS is isomorphic to the other side dual Zuckerman functor Z hat S upper R. This follows from the observations on the previous slide and the snake lemma. Indeed, the functor CS is defined at the cokernel of the natural transformation between two exact functors, and the kernel of this natural transformation is exactly this other side dual Zuckerman functor. So dually, we can consider the right-derived functor RKS. This is an endofunctor of the boundary derived category of O0. And we have the dual statement that all cohomology functors of Ks of degree greater than 1 vanish, and that the degree 1 cohomology functor is exactly the other side Zuckerman functor. And this follows from the previous claim by using the duality, since Cs and Ks are connected by conjugation with a simple preserving duality. Next, let us describe these derived functors in terms of complexes of functors. So we can consider the following two complexes of functors. The first complex, called Cs, has theta s in homological position 0. Theta e, this is the identity functor, shifted by -1 in homological position -1, and they are connected by the adjunction morphism adjunction lower s. The complex Ks has theta s in homological position 0, the identity in the homological position 1, shifted by 1 in degree, and they are connected by the natural transformation adjunction upper S. It is not very difficult to show that the derived functor LCS is isomorphic to applying the complex Cs to an element in the derived category and then taking the total complex. Similarly, the right-derived of the co-shuffling functor is isomorphic to applying the second complex Ks and then taking the total complex. And the usual terminology is that these complexes are called either Ricard complexes or Roquia complexes. They appeared in the following paper by Ricard from 1994 or the following preprint by Roquia from 2004. The next claim about the shuffling functors is that the corresponding derived functors are mutually inverse equivalences of the boundary derived category of O. So here is a sketch of the proof. Adjointness of these two functors implies adjointness of the corresponding derived functors. Next, we can observe that for any module M with Vermont flag, the adjunction morphism from this module to the composition of Cs followed by Ks applied to this module, this adjunction morphism is an isomorphism. And from our description of the cohomology functors, it is easy to see that the composition Ks-Cs is actually acyclic on modules with Vermont flag. Hence, the adjunction morphism from identity to the composition of the left-derived Cs followed by the right-derived Ks, the evaluation of this adjunction morphism at each projective module P is an isomorphism. So this means that this composition, left-derived of Cs followed by the right-derived of Ks, is isomorphic to the identity on the boundary derived category of O. By a dual argument, the evaluation of the adjunction morphism from the composition of the right-derived of Ks followed by the left-derived of Cs to the identity at any injective object I is actually an isomorphism. Therefore, this composition is also isomorphic to the identity functor on the derived category. And this together proves this theorem. Let us now look at what kind of linear transformations the shuffling and co-shuffling functors induce on the level of the Grothendieck group. Recall that the Grothendieck group of the category O0, which is isomorphic to the Grothendieck group of the boundary derived category of O0, is isomorphic to the free abelian group with the basis given by the elements of the Weil group. And this isomorphism is given by sending the class of the Vermont module delta W to W. Recall also that the split Grothendieck ring of the category P00 is isomorphic to the integral group algebra of W by sending the class of the indecomposable projective functor theta W to the element HW underlined of the corresponding Kazhdan-Lusztig basis. The derived functor LCS is of course a triangulated functor, and therefore it induces a well-defined linear transformation on the level of the Grothendieck group of the boundary derived category of O0. So the claim is that this linear transformation is given by the right multiplication with the simple reflection S. Indeed, from the description of LCS via Roquier-Ricard complexes, we have that the linear transformation induced by this functor is equal to the linear transformation induced by theta S minus the linear transformation induced by the identity. Of course, the linear transformation induced by the identity is just the right multiplication with the identity, while we know that the linear transformation given by theta S is the corresponding ungraded Kazhdan-Lusztig basis element. So it's a multiplication with E plus S. So now if we subtract this, we get exactly the element S. Clearly, we have exactly the same property of the right derived of the Koszaflin functor. So we can deduce from this that the linear transformation induced by the left derived of the Szaflin and the right derived of the Koszaflin functor on the Grothendieck group of the bounded derived category, these linear transformations coincide. However, the two functors, of course, are not isomorphic. They are exact on different sides. Another observation is that the square of the linear transformation induced by LCS is the identity. But of course, the square of the derived functor LCS is not the identity, because CS, for example, kills the dominant simple module. Let us look in more detail at the SL2 example. So consider the projective resolution of the injective module nabla E for SL2. So the claim is that this resolution, nabla E, is covered by PS, the kernel is covered by PS, and then the next kernel is just PE. So here is an explicit graded picture. Here we have in magenta our module nabla E, so it's covered by PS, then the kernel S is covered by PS, and now the kernel ES is exactly PE. So this is a projective resolution of nabla E. If we want to compute the left derived of CS applied to nabla E, we should apply our functor CS to this projective resolution. So the functor CS sends PS to PS, it shifts it by 1, and it sends delta E, which is PE, to delta S. So the outcome will be this complex. So the only difference is that it's shifted by 1, and then this ES becomes E. But this in particular means that we get this homology. So of course, on the level of 0 homology, we just get nabla E shifted by 1. Then we will also have the first homology, which is here E, in homological position minus 1. Braid relations for Szaflin functors have the following consequence. The assignment, the simple reflection S, goes to the left derived of the Szaflin functor CS, gives rise to an action of the braid group associated to our while group W on the bounded derived category of O0 and on its graded version by autoequivalences. And this action was one of the prototypical examples for Roquier's definition of a two-braid group. Please note that this is indeed an action of a braid group and not of the while group W, because the square of LCS is certainly not isomorphic to the identity functor. So in fact, if we apply the square of this derived functor to the dominant simple LE, we get this dominant simple LE shifted by 2 in homological position. And in the graded version, it will also be shifted in degree. Other interesting functor from this action, which we will see later on in the course, are the left derived of the Szaflin by the longest element and the square of these functors. So these are important functors, which we will see later. So next, let us discuss the Szaflin on the level of parabolic category O. Let P be a parabolic subalgebra of G containing the Borel subalgebra H plus N plus. Consider the corresponding parabolic category OP and its principal block O0P. Note, all projective functors preserve OP. Therefore, both the Szaflin functor CS and the Koszaflin functor KS restrict to O0P. Also, both the left derived of CS and the right derived of KS restrict to the bounded derived category of O0P. A warning, the derived functor of the restriction of shuffling and co-shuffling is not usually isomorphic to the restriction of the derived functors in general. So here is an extreme example. If P is equal to G, then the restriction of Cs to O0P, which is just the additive closure of the dominant simple module, is 0, while the restriction of LCS to the bounded derived category is still an auto-equivalence. A more subtle example is given on this next slide. Consider the SL2 parabolic in SL3. So in SL3, the while group consists of E, S, T, ST, TS, and W0. And we take the parabolic such that the corresponding parabolic subgroup in W consists of E and S. Then the elements which survive in the parabolic subcategory are E, T, and TS. So these are the indices of simples which survive in the parabolic subcategory. Let us compute the left derived of the restriction of the T shuffling to the parabolic subcategory applied to the dominant simple module. So one can compute the projective resolution of LE. So LE is covered by its projective PE in the parabolic. The kernel is covered by PT in the parabolic. The next kernel is covered by the direct sum of PE and PTS. Then the next kernel is covered by PT, and the final kernel is just PE. So here is what happens if we shuffle the parabolic projective modules. So the shuffling of PE gives us delta T in the parabolic. The shuffling of PT gives us PT back. This is because its socle is not killed by theta T. And shuffling of PTS gives us nabla E. So now if we use this property and apply it to the sequence, we get such a sequence. And in this particular sequence, one can see that we have homology LE at the homological position -1, but then we also have homology LTS at the homological position -4. So here we have the map which sends the top of this module to the socle of this module, but this module is not simple, it has TS beneath it. So it will have homology TS at this position. So the derived length of LCT restricted to parabolic is at least 4. And for the usual category O, it is 1. Shuffling and co-shuffling is also defined in the setup of S subcategories in O. So let P again be a parabolic subalgebra as before. Then we can consider the corresponding S subcategory SP and its principal block SP0. We know that projective functors preserve SP, which means that both shuffling and co-shuffling restrict to SP0. And again, both derived shuffling and derived co-shuffling restrict to now not the bounded derived category, but the category of perfect complexes over S0P. So the homotopy category of bounded complexes of projective objects. So in order to see this, we need to use that S0P is a Gorenstein category, which we saw. So injective objects have finite projective dimension here, and vice versa. And in this case, we actually will have that the derived functor of the restriction is isomorphic to the restriction of the derived functors, because the S subcategory corresponds to a centralizer subalgebra, and so we can define everything in terms of complexes of projective modules in the original category O. Let's finish with some questions for PhD students. Question number 1. Provide all the details for the claim of the commutativity of the solid square in the proof of the lemma about the jointness of CS and KS. Question number 2. Prove with all details that the maps given in the short exact sequences for translations of Vermont modules are given by adjunctions. Question number 3. Prove commutativity of shufflings for commuting simple reflections. Question number 4. Fill in all the details in the proof that LCS is a self-equivalence of the bounded derived category with inverse RKS. Question number 5. Determine the combinatorics of the linear transformation of the graded bounded derived category induced by the derived shuffling functor. Thank you very much, and see you next time.